As we learn the different topics in AP chemistry, it's really convenient for us to separate them and think about just one thing at a time, about the enthalpy, about the entropy, about the free energy before we put them together. And free energy is telling us how likely is something to turn into something else. That's very closely related to equilibrium as well. Depending what chemicals I have, they are either more or less likely to turn from reactants to products or products back to reactants. The example that I have here is the reaction of nitrogen and hydrogen to make ammonia. If I have a whole bunch of just nitrogen and hydrogen, it will not stay like that because of the thermodynamics, because of the change in energy and entropy. It will likely collide and turn into some ammonia. But that doesn't mean that it turns into ammonia and stays as pure ammonia. Because if I have pure ammonia, those are just as likely or likely in similar ways to collide into one another, turning back into nitrogen and hydrogen. So having all products in this reaction is not favorable thermodynamically. Having all reactants is also not favorable thermodynamically. We really have a mix of the two of them. And each reaction has kind of a unique mix based upon the temperature, sometimes the pressure, and other conditions. That's what equilibrium is all about, our ratio of products to reactants. That connects very much so with how likely it is for something to change into something else, or the thermodynamics. Reactions that have a lot of products, we say, are very likely to react, or the forward reaction is very favorable, and we would define that as a negative delta G or a fairly large K. Anytime we're in double, triple, quadruple digits or bigger in terms of K, and we've got a significantly negative value for G, we would say this reaction has a whole lot of products relative to the amount of reactants. Going backwards in reactants is much less favorable. Some reactions aren't very favorable in that forward direction. The reactants are much more likely to stay together. The process of turning into products is thermodynamically unfavorable, and that ends up with the K less than 1. Our equilibrium greatly favors our reactants. But some reactions, and occasionally these are described as a true equilibrium, have a close to equal mix of everything. That's when you have a delta G that's not very negative nor very positive, meaning that both directions are very similar in their favorability in terms of energy. And that's when we have a K pretty close to 1. Pretty close to 1, I would say, is kind of in that 1/10 up to 10 range. So anywhere there where we're maybe talking about a single digit value, or when we're talking about a decimal between 0.1 and 1, that's fairly close to 1. And that's going to end up with the delta G that isn't too big in either direction. When we're doing this, we have these equations that can connect them. The delta G is negative RT ln of K, and that connects this positive sign with something that is less than 1, or this negative sign with something that's greater than 1. And we can undo our natural log by doing an exponent here with E. A lot of times you could be given numbers and asked to do the math. We would be thinking in terms of Kelvin, and our R, we would use the 8.314 joules per mole Kelvin, meaning that our delta G would come out in terms of joules. And same idea over here. But we also just want to make this relationship of the negative delta G, negative right here, happens when our K is greater than 1. But maybe more significantly here, when I take the natural log of a decimal, the natural log of a decimal is a negative number. A negative times a negative gives me a positive. So this equation is given, but we also have to remember just what that means. So there's lots of different ways we can think about this. This equation is super valuable, but also thinking about it in terms of maybe our particulate diagrams. Do I have all this, or a mix of them? How can I show that in terms of a graph? How are all of these different things here? They will not specifically ask you to do a lot of calculations, Understanding what it means to have a big K, a small k, or comparing our Q to our K with Le Chatelier's principle is an important way of understanding our reactions.